We present STRAIDE, a research platform for shape-changing spatial displays based on actuated strings. My name is Severin Engert, and this is joint work together with Konstantin Klamka, Andreas Peetz, and Raimund Dachselt, all from the Interactive Media Lab in Dresden. A lot of HCR research is looking for novel approaches beyond graphical user interfaces, with a focus on other qualities like appearance, calmness, or tangibility. For our work, tangible and shape-changing interfaces are particularly promising, as they give physical access to digital data through direct manipulation. However, these are often complex and monolithic systems. Therefore, we see great potential in modular approaches and toolkits, which overall simplify prototyping and exploration. On the other hand, we are inspired by the flexibility and appearance of string-based installations, but we would like to bring them from stages and other large-scale applications to everyday spaces. This would render situated visualizations with direct interaction possible. With these inspirations in mind, we developed STRAIDE, a string-actuated interactive display environment. STRAIDE allows to prototype and evaluate spatial displays with string actuation. We developed modular hardware made from readily available components and added functional elements to create interactive physical user interfaces. To further ease the application development, we additionally provide a set of easy-to-use software tools. In detail, our main contributions are a design rationale for string-actuated spatial displays in everyday spaces, a comprehensive research platform with modular hardware and tailored firmware and software. We demonstrate the usefulness of our toolkit in different real-world scenarios. And in the paper, we also evaluate insights from our iterative development and discuss feedback from application developers. As highlighted in the beginning, our work relates to research fields like data visualizations and physical user interfaces. First of all, we looked at shape-changing interfaces and 2.5D pin arrays. These are often complex prototypes with hundreds of physical bars, as for instance in the eMerge system. For us particularly interesting were also modular approaches, like shape canvas with shape clips. As our intended visualizations are quite similar, we further studied mid-air interfaces, with for instance magnetic levitation, as showcased by 0M. However, we wanted to rather employ a much simpler string-based actuation, as demonstrated by artistic installations for stages or showrooms, here for instance breaking wave or kinetic lights. For STRAIDE, we aim to combine the advantages of these approaches. We want to create a real user interface with direct interaction, but we would also like to achieve the magical appearance of mid-air visualizations, while making use of large strokes with fine granularity. To achieve this, we investigate the design parameters of such string-based systems. These affect its configuration, appearance, or functionality. To create mid-air visualizations, we first thought about different elements. These could range from passive shapes of different materials to elements with embedded electronics or complex internal structures. Next, we want to have modular actuators that can be arranged in different layouts, or wherever they are needed for situated use cases. These two combined could enable physical visualizations. We focus on casual visualizations with only a few elements and ways to combine individual elements into symbols and other expressive content. To create a user interface, we want to add interaction to our system, where we mainly focus on direct interaction, for instance with touch or drag, but we also consider combinations with smart devices. Based on these design considerations, we iteratively designed the physical components of our toolkit. We aim for a modular structure to facilitate the exploration of situated use cases with different physical setups. Additionally, we kept fabrication as simple as possible so that researchers can easily rebuild our toolkit. We began by testing different actuators and went with stepper motors due to their fine granular actuation. During initial tests, we studied their properties to infer precise position control for our tailored firmware later on. After committing to NEMA 14 steppers, we iteratively developed space-efficient mounts. They are made from laser-cut acrylic containing the motors, a limit switch, and a roller mechanism which uses a braided line to lift the attached element. As we want to achieve dense arrangements, we stacked 4 actuators in a motor tower to create these self-contained units. You only have to add power and Ethernet, and then you can actuate 4 elements individually. To prove their versatility in different scenarios, we applied these actuation units to 3 different physical setups. We have tested 1 tower in a home environment, 4 towers on top of a whiteboard, and 16 towers in a dense matrix arrangement with over 64 actuated elements. To support diverse visualizations, we fabricated and tested a variety of elements. These range from passive geometries to shape-changing, illuminated or even interactive objects. Now we can combine actuators and elements into a specific spatial display. However, creating meaningful visualizations and custom applications remains challenging. To simplify control over many connected actuation units, we added a central Node.js server, which handles the hardware control. In combination with our STRAIDE libraries, custom applications can easily operate the physical interface using WebSocket communication. For remote development in desktop environments, we developed the platform Emulator. It replicates the hardware and its interface and can be used for application development on regular screens or even stereoscopic displays. Additionally, we contribute augmented reality previews. Developers can use AR glasses to view an envisioned device or application in its intended environment. This helps to judge appearance and ambience. Finally, we sought how to simplify the ideation process and how to involve users without programming expertise. Therefore, we developed our Visual Designer. It is a web-based tool for sketching ideas on 2 canvases, with a live preview directly on the device. All these software components can be interchanged due to the versatility of the WebSocket communication. Overall, this simplifies the challenging ideation, design and development of novel applications for such 2.5D shape-changing interfaces. To show the feasibility of our hardware and software toolkit, we developed several real-world applications using the previously presented instances. In our single setup, an individual element is used to show ambient information. Here, the water drop conveys the water level of this plant. Here's another example using our linear setup. The physical line augments the hand-drawn sketches on a whiteboard, and with direct interaction, the user can adjust the dynamic graph. The weather application shows different conditions like sunny or rainy weather, but as ambient visualizations. Multiple applications using this matrix setup were implemented by a team of students. After 1 semester-long practical course, they evaluated our software tools, and details on their feedback can be found in our paper. To conclude, our STRAIDE research platform enables rapid prototyping of shape-changing spatial displays. Therefore, we provide modular hardware and versatile software tools, which we already evaluated in several real-world scenarios. With this, we hope to simplify the exploration of situated physical visualizations in the future. We want to further work on and extend this toolkit and would love to test it with practitioners. Therefore, we published all development resources on our project page. Further details can also be found in our full paper. Thank you for your attention.